So today we begin talking about our last module here, which is going to be about the broader universe in general. So we've kind of been working from like a smaller scale on Earth all the way out to kind of our biggest scale here. And the first thing that we're going to talk about with regards to the universe is the sun. And this is really kind of like our introduction to stars, because the sun is the most important star to all life on Earth. And it's composed of many different layers, and we're going to be talking about each of them individually. You should have this diagram printed in your notes. The first thing we're going to talk about is we're going to talk about the innermost layer of the sun, and that is the core. And the core is extremely dense. It's made out of plasma, like most of the sun. And because it is so dense and it's under so much pressure and it's at such a high temperature, nuclear fusion of hydrogen will spontaneously occur. And that's what makes a star, essentially, is that you have all of this hydrogen gas and it gets to be under enough pressure and temperature that nuclear fusion begins to take place. And that's what produces all the energy and light from the sun, is nuclear fusion in the core. And the core tends to be like 14.5 million Kelvin. So we're talking insanely high temperatures here. But the core is the hottest, densest, and innermost layer of the sun, and that is where nuclear fusion is taking place. So as we start to move out from the core, the next layer is what's called the radiative zone. And it's called that because in this layer, energy is transferred by radiation. So essentially by electromagnetic waves. And energy tends to move very, very slowly through this layer. Again, partially because of the density. In fact, a single photon, so a single particle of light, can take 200,000 years to move from the core through the radiative zone and out into space where you can actually see it. So energy moves very, very slowly through the radiative zone. And the radiative zone is a little bit cooler than the core. It tends to be more like 2 million degrees Kelvin. Which, to give you a sense in Fahrenheit, that's like 12 to 4 million Fahrenheit. So still insanely high temperatures, but not as hot as the core, which is kind of what we'd expect, right? Like we would expect where the energy is being produced to be the hottest, and as we get farther away from that, to be cooler. After the radiative zone, we get the convection zone. And it's called the convection zone, unsurprisingly, because energy is transferred by convection. So convection is a process of energy transfer where you have like a hot fluid rises to like a cooler place and then cools off and sinks again. So in this case, it's the plasma that's moving. So hot plasma close to the radiative zone rises up towards the top of the convective zone, it cools off, and then it sinks back down again. So you'll kind of have like this kind of looping. So it rises up towards the top, cools off, and then sinks again. And then it'll rise up towards the top, cool off, and sink again, and so forth. And so you get this flow of plasma through the convection zone. It's the same process by which a lava lamp works, right? So like the fluid in a lava lamp warms up, rises to the top, cools off a little bit, sinks back down, warms up, etc. And plasma, since we're talking a lot about plasma, we should talk about what plasma is. Plasma is the fourth state of matter. It's not one that we typically encounter here on Earth, but you can. Usually it has to deal with like lightning or producing it in like an electrical device. But plasma is the most common state of matter in the universe because that's what stars are made of. And basically it's, if you take a gas and you get it really, really hot, its electrons will start to be stripped away and kind of be loose and fluid. So plasma is kind of this like superheated gas where like the nucleus of the atoms and the electrons are just kind of all flying around and mixed up. And so you have like, it has a charge, basically. And we're looking a little bit cooler than the radiative zone, like 3.5 million Fahrenheit. And this is like another diagram of convection here. So you can see here the red arrows are showing the warm plasma rising up, and then it cools and sinks. And you have that whole cycle throughout the entire convection zone. I think that diagram's in you guys' notes as well. So after the convective zone, we reach the photosphere, which is essentially the surface of the sun. It is the deepest layer that we can directly observe. So this is the first part of the sun that you can actually see from Earth. And it's where the light that was produced in the core finally reaches space. And this photosphere extends from the surface to about 250 miles above the surface. And as expected, it's cooler than the convective zone, like 6,000 degrees Kelvin, which is somewhere around like 11,000 to 6,700 degrees Fahrenheit. So still crazy, crazy hot, but much cooler in comparison to those inner layers of the sun. So next up is the chromosphere, which is this transparent layer over the photosphere. And it's basically what it says there. It's a transparent layer of gas, again, mostly hydrogen, because that's what the sun is made out of, is it's primarily hydrogen gas. And again, the chromosphere extends from 250 miles above the sun's surface, so the end of the photosphere, to about 1,300 miles above it. So it's a relatively thick layer. And the interesting thing about the chromosphere is that its temperature starts to behave in a really weird way. And it only gets weirder when we get to the corona. So we, in our everyday experience, like if you have like a source of energy, like a source of heat, like it should get cooler the farther away you are from it, right? Like if you got a campfire, if you stand right next to the campfire, it gets really warm. But if the farther and farther you get away from the campfire, the less warm it feels. And so far, the sun has kind of showed that, right? The core was the hottest and it got cooler and cooler as we go out. However, the chromosphere starts to get hotter the farther it is away from the sun's surface. So at the end of the photosphere, like 250 miles above the surface, it's more like 6,700 degrees Fahrenheit. However, when you get to the top of the chromosphere, like 1,300 miles, it's more like 14,000 degrees Fahrenheit. So it starts to get a little funky with that. Even more so with the corona. The corona is essentially the sun's atmosphere, and it is way, way hotter than the photosphere or the chromosphere. Much, much hotter. It's like 900,000 degrees Fahrenheit. And the interesting thing is, we're not totally sure why the corona is so much hotter than the photosphere and the chromosphere. But the Parker Solar Probe that was launched, I think, a couple of years ago, like that's one of its main things that it's trying to study is the corona to help us figure out why is the corona so much hotter than like the photosphere and chromosphere? Because in, you know, our basic everyday experience, that doesn't make sense. But the corona is the outermost layer of the sun. A lot of times people call it the sun's atmosphere. And it begins about 20,000 kilometers above the sun's surface where the chromosphere ends. Oh my goodness, why are all these slides have different units of distance and temperature on them? I'm gonna have to go through and edit that. Anyway, sorry, it's a side note. Another interesting feature of the corona is because it's kind of this thin, wispy outer layer, you can actually only observe the corona during a solar eclipse. So during a full solar eclipse, the little bit of wispy light that you guys see around the black disk of the sun, that is the corona. Now, there are also imaging devices that have been made that essentially like block out the disk of the sun for you so you can study and photograph the corona. But before those were invented, the only time you got to see the corona was during a solar eclipse. So now let's talk about solar radiation. So first off, radiation is a broad term that just means energy. If something is emitting radiation, it's emitting energy. Now, energy emitted as radiation can be a couple of different things. It can either be a particle, or it can be a wave, like visible light. And the sun emits both. It emits lots of different electromagnetic waves as radiation, and it emits particles. And we're going to talk about all of them. Obviously, the sun is emitting visible light. Visible light is what we can actually see. So visible light is defined as the wavelengths of light that our eyes can perceive. And this photo here on the left at the bottom, this is a picture of the sun's surface in visible light, which kind of matches what we would expect. You know, here on Earth, even through the atmosphere, we just kind of see it as, you know, a big round ball without a lot of features. Many more features of the sun, particularly of the photosphere or chromosphere, or sometimes the corona, can be viewed better through different wavelengths of light. So the sun also emits infrared radiation, or sometimes called IR. And that is essentially like heat energy. So the warmth that you feel when the sun is shining on you, that is IR, that's infrared radiation. And this picture at the top is an image of the sun in IR, where I think the darker spots on this are hotter spots, and then the lighter ones are cooler ones. The sun also emits UV radiation, or ultraviolet. Ultraviolet light is what gives you a sunburn, because ultraviolet radiation, unlike visible light and IR, has enough energy to start stripping electrons off of cells. It's a form of what we call ionizing radiation. And it's ionizing radiation that can be harmful for you. Which is why, you know, if you stay out in the sun too long without sunblock, you're going to get a sunburn. Because the ultraviolet light has enough energy to damage the cells in the outer layers of your skin.
I watched a video that it was like the doctors saying that you should always wear sunscreen, like even if it's cloudy, and like moisturize every single day if it can ruin your skin.
So, yes, that to an extent, yes, that is true. So like even like right now in the summertime, even if it's cloudy, you should still wear sunscreen because ultraviolet radiation is not blocked by clouds. It's more the visible light and the IR that can get blocked by it, but ultraviolet is not. For us in the wintertime, since we're in the northern hemisphere, especially since we're fairly far north. Sunscreen's probably not super important in the wintertime. I mean, for most of us, our entire bodies are probably covered if we're outside in the snow and stuff. And you gotta, the angle that the sun makes with the northern hemisphere in the wintertime is very, very weak. But yes, if you were really concerned about making sure your skin was like really thoroughly protected, yeah, you might still put like some kind of light sunscreen on in the winter. That's why most moisturizers like have a sunscreen in them. But if it's me, I only worry about it in the summer when I'm wearing like short sleeves and shorts, and you know, the sunlight's very direct on us. But yeah, in the summertime, even if it's cloudy, still wear sunscreen because you can still get a sunburn. But yeah, good thing to bring up. And the sun emits all of these types of light all at the same time. So all of these different wavelengths of light are being emitted by the sun all the time. And these are probably the three that we're most familiar with because they're the ones that like we physically interact with. You know, like we see sunlight, we can feel its warmth. I'm sure everyone has had the unpleasant experience of a sunburn. But this isn't the only wavelengths of light that the sun emits. There are other wavelengths that are equally interesting to scientists. First off is radio waves or radio emissions. So these are very like long wavelengths. And again, they're non-ionizing radiation. They can't really be harmful. But we do a lot of studying of the sun and other stars with radio telescopes. And a radio telescope is going to look like a giant satellite dish because it's just trying to pick up radio waves from the sun or stars. And radio waves are useful because they correlate with sunspots, which we'll talk more about in a little bit. So typically if there are more sunspots, you're going to pick up more radio waves coming from the sun. And if there's less sunspots, you will have fewer radio waves. So this right here is an image of kind of radio waves emitted by the sun. And you can see here where it's a little bit brighter, that's where we're picking up more radio waves. It's a slightly more active area of the sun. The sun also emits X-rays. And X-rays are really important, particularly for studying solar flares. And a lot of objects in the universe at large are X-ray sources. So most stars are emitting some kind of X-rays. Black holes also emit large amounts of X-rays. So X-ray astronomy is like a whole branch of astronomy where you're just looking at X-rays from space, basically. Sometimes it's also referred to as high-energy astrophysics because X-rays are also a high-energy form of ionizing radiation. Fortunately, the Earth's magnetic field blocks a lot of the ionizing radiation from the sun. But here you can see the bright spots in this image are the spots where the most X-rays are being emitted from the sun. The sun also emits particles. Like I said before, radiation can come in the forms of electromagnetic waves or as particles. And one particle emitted by the sun are neutrinos. And neutrinos are interesting because they're almost massless. Like their mass is so tiny, it's almost undetectable. And because of that, they're a byproduct of fusion reactions. So as fusion reactions are happening in the core of the sun, neutrinos are being produced. And because they're nearly massless, they tend not to interact with other forms of matter. So there are millions of neutrinos passing through us and passing through this room right now, but like you would never feel them or notice them because they simply don't interact with the matter in our body or the room. Now let's talk about solar activity. And so this is the stuff that's also interesting because it can have a direct effect on our everyday life. Now, the sun goes through a roughly 11-year cycle of activity. And when the sun is least active, we call that solar minimum. And when the sun is most active, we call that solar maximum. And you can make some basic predictions based on previous cycles of when this is going to happen. But usually like solar minimum and maximum for a particular solar cycle is defined like after they've happened. Because then you can actually look at the data and be like, yes, this right here, that was the lowest activity of the sun there. And here's like an image that we can kind of look at here. So these top images are taken with visible light, and these bottom ones are in ultraviolet. And so here we have on the left, we have solar maximum from July 19th of 2000. So this isn't the most recent solar cycle. It's like a solar cycle before the last one. But you can see that here at solar maximum in visible light, you can see lots of little dark spots. Those are sunspots. But here at solar minimum, which is March 18th of 2009, you can see essentially no sunspots. The difference is even more dramatic when you look at the sun's ultraviolet images. Here you can see all kinds of activity and bright spots at solar maximum. And then at solar minimum, like nothing. It's almost perfectly uniform. And this full cycle of solar minimum, solar maximum happens about every 11 years. I think the full cycle is defined as like from one solar minimum to the next. I think that's how they like mark as a new cycle has started. And so solar maximum occurs about halfway through that, which is why the solar minimum here is from 2000 and the solar maximum is from 2009. All right, so let's talk about solar activity, some types of it. The most common type of solar activity that you'll hear people talk about are sunspots. And sunspots are areas where the sun's magnetic field lines actually like pierce or poke holes in the photosphere, the surface of the sun. So there are little holes that kind of open up in the photosphere. And sunspots appear dark on the surface of the sun because they're slightly cooler than the areas that surround it. And so all the little dark spots that you see in this image here, those are sunspots. And they are one of the most basic things you can do to look at how active the sun is. More sunspots, the sun's more active. Less sunspots, the sun's less active. And that's because sunspots are almost always accompanied by other types of solar activity. For example, solar prominences. A solar prominence is when a huge loop of plasma is ejected from the sun. However, the key feature of this is that it stays anchored to the surface of the sun. So it's still going to stay anchored to the photosphere, but it's projected out, and it's this big loop. And that's a solar prominence. So when it's connected to the surface of the sun, it's called a solar prominence. Sometimes you see similar features in the corona, and those are coronal loops or coronal holes. But a solar prominence is always still attached to the surface of the sun. Next up is a coronal mass ejection, or CME. And these are probably one of the things that, one of the biggest reasons for studying the sun, because they can be very detrimental to our everyday life here on Earth if a strong one hits Earth. Especially nowadays, because so much of our life is based off of electronics and electricity. So a coronal mass ejection, or CME, is literally a large bubble of gas, matter, being ejected from the sun. And it tends to leave it or being ejected from the corona specifically. And it tends to like spread out as a fan. So this big fan-shaped piece of the image there, that is the CME. And CMEs can be like really damaging, right? Because it's a cloud of gas and charged particles. And those charged particles can induce current in electrical wires. So if a strong enough CME hits Earth, it can cause surges in power lines, overwhelm an electrical grid, and cause widespread blackouts. In the 1800s, Earth was hit by an extremely strong CME, and fortunately at the time, the only real electronic type of communication was telegraph. But the charged particles from the CME induced so much current in telegraph lines that they spontaneously caught fire all around the country. And so telegraph service was disrupted for a while. Now imagine nowadays with the amount of electronic communication that we do, what kind of disruption that would have. A lot bigger than it did back in the 1800s with the telegraph system. Fortunately for us, because CMEs are made of matter, like they're literally charged gas particles, they don't travel very fast. It's going to take usually about 3 days for a CME to hit Earth, which means if a strong CME is detected ahead of time, like when it first leaves the sun, we can prepare for them. You know, power grids can reduce the amount of current going through lines or have planned blackouts so that, you know, you don't have transformers and stuff exploding from the excess current. So it is something that we can prepare for, and it's one of the many reasons why NASA keeps a very close eye on the sun. The charged particles from a CME will also interact with Earth's magnetic field and cause auroras, so northern or southern lights. Solar flares are another troublesome bit of solar activity sometimes for us. A solar flare is just an intense burst of radiation, so a huge burst of energy from the sun. And they appear as bright areas on the sun. Here is an X-ray image of the sun, because solar flares tend to have a lot of X-rays in them. So this really, really insanely bright part, that is the solar flare coming off the sun right there. And they are the largest explosive event that takes place in our solar system. So within the solar system, there's nothing larger, more explosive, or more energetic than a solar flare. And a solar flare is made entirely of energy. So that's kind of the biggest difference between a CME and a solar flare. Is a CME is literally made of matter. It's actual gas and charged particles. But a solar flare is just energy. So we're just talking like X-rays, visible light, ultraviolet, IR. It's just energy in the form of waves. Because of that, a solar flare will reach Earth in 8 minutes because the energy from a solar flare is traveling at the speed of light. Solar flares can also be problematic on Earth because they can interact with radio waves on Earth and microwaves, which is pretty much what all of our communication runs off of, is radio and microwave frequencies. And it can also cause disruptions with like navigation because it can disrupt like GPS satellite communications as well. And so they can be really problematic, but again, it's usually not as lasting, right? So like a solar flare, it can interrupt our communication and our navigation, but typically like the solar flare passes relatively quickly. And again, because it's just energy, it can't affect power lines the way that a CME can. So let's talk about how the sun produces energy. Nuclear fusion, we'll talk a little bit about it. This is just going to be like a real basic level explanation of nuclear fusion. And basically what you have is hydrogen atoms. Because they're under such high temperature and pressure, they spontaneously fuse together to create helium. And that fusing together releases energy. So here in this diagram, you can kind of see right here we start with kind of two hydrogen nucleuses, and they combine together, and part of that releases another type of subatomic particle called a positron. But this is also where neutrinos get released. After you have those two hydrogen nucleuses fused together, that gives you a neutron. So you have a hydrogen nucleus that now has a neutron in it. And that will combine with another plain hydrogen nucleus and release lots and lots of more energy, including gamma rays. And that is what will end up with our helium nucleus there. So that's kind of just like a real rough, basic overview of how energy is produced in the sun.